Assalamu alaikum everyone. So in this video I would like to share how do we construct a multiplexer, a simple multiplexer in Xilinx using Verilog HDL. So in particular we will utilize the case statement and the always block. So the combination between always block and case statement can realize the implementation of multiplexer. So let's choose this simple multiplexer. So this is basically the 4-to-1 multiplexer with 4 inputs. Let's say this is I0, I1, I2, I3 and 1 output, of course. So this multiplexer has 2 bit selectors, so S1 and S0. Okay, so the inputs I0 up to I3 are correspond to the input to the system, which is A and B. So each A and B is 1 bit signal. So I0 basically equals to A and B, I1 equals to A or B, I2 equals to A XOR B, I3 equals to AX nor B. So Y, the value of Y, will be decided according to the values of S1 and S0. So this is the function table that describes our multiplexer circuit. Okay, let's begin with our Xilinx project. So maybe we can place these two windows side by side. Okay, so let's create a new project and let's name it as Max for 1, for example, or Max 4, just Max 4. Next, and we can choose the Spartan 3 starter board and make sure the preferred language is Verilog and finish. So we right click on here and we choose a new source, which is the Verilog module. So we can name our module as Max 4, and we can skip this stage for the time being because we will specify everything inside this module. Okay, so we have the skeleton of the module. So obviously we have 3 inputs, which is S, A and B, but S is a 2-bit variable or input. So input 1 down to 0, S means that S consists of S1 and S0. Input A, B, because A and B are 1 bit, and output Y, because Y is 1 bit as well. Okay, next. So the content of the module is basically consists of the description of this function table. So we can begin with always block, always alias, braces, begin and end. Okay, so inside these braces or the brackets, we will list down the what do we call the sensitivity list, in which what kind of variable, this block must be executed according to the changes of what variables inside these braces. So obviously any changes in A or B or S will make this block to be executed. So we can specify inside this always block by using the case statement. So case, so obviously S is the case variable. Okay, so we have 4 combination of S, 0, 0, 0, 1, 1, 0, 1, 1. So we can write down here, so if S is 2-bit binary 0, 0, so what happened? If 2-bit binary 01, what is the corresponding function? If 2-bit binary 1 0, what should be executed? If 2-bit binary 1 1, what will happen? So obviously, if S00, Y should equals to A and B. Sorry. If 0 1, Y equals to A or B, according to this table. If 1 0, Y equals to A, X or B. And finally, if 1 1, if S is 1 1, Y equals to A, X nor B. So X nor is not is equals to not AX nor B. So we can also place a line to define the default value of the outputs. So let's place default Y equals to 0. By default, Y is 0. So we can end our case block with AND case. Okay. AND case and always AND module. That's it. So we have accomplished our 4-to-1 multiplexer. But bear in mind that since Y appears inside this always block, it must be declared as register as well. So we place output register Y up here. So we can save our project. And then we can compose the test fixture to verify our module. So new source, test fixture, marks for the F, finish. So this is our test fixture. So we can remove this. Okay, down here we can add the stimulus. So obviously the inputs are S, A and B. So since S is 2-bit, A is 1 bit, B is 1 bit, the total number of bits between them is equals to 4. Means that they should produce the 4-bit combinations in which there are 16 different combinations between from 0 0 0 0 up to 1 1 1 1. So means that if we write in this manner S A B by using the concatenation 4-bit binary, so S A B will begin from 0 0 0 0 up to 4-bit binary 1 1 1 1. So the idea is like this. We want to simulate such that SAB from 0 0 0 and then 0 0 0 1 up to 1 1 1 1. So we can realize this kind of implementation by using the for loop. So let's write like this. For, let's choose one integer because this is equals to 0. This is 0 in decimal representation. This is 15. So we can use, let's say, k. For k equals to 0, k less than 16, k equals to k plus 1, begin. S A B equals to k for a duration of let's say 10 nanoseconds. So we can end our for loop. But let's not forget to declare the integer k up here before the initial initial begin integer k. So we can save our project. So what is this? Integer k. All right. So maybe we can end the stimulus with finish. So finish. Okay, let's run our test fixture. So go to this simulation option, click on the test fixture file, and then we can find this behavioral check syntax. So it takes a few seconds to accomplish. So everything seems alright, so we can launch the simulation. So this is the text fixture code. So the graph is over here, down here in this tab, and then let's see the full view. So we can see there is Y, of course, the output. So maybe we can rearrange this, and we can remove K. Okay, let's examine our results. Our simulation results. So S00 means Y equals to A and B. S01, Y equals to A or B. S10, Y equals to A XOR B. If S11, Y equals to A XOR B. So obviously this is all correct, because for AND only this combination that will produce output high, in which A equals to 1, B equals to 1. So this is correct. For OR combination, only this combination that will produce output 0, A0, B0, else Y equals to 1. For XOR, if A and B are differed, if A difference with B, output is high. So this is correct. For XNOR, it is the inverse of the XOR. So everything is fine. So that's all for now. So I hope you can utilize this always block and case statement to produce a multiplexer. So thanks for watching.